In this video, we'll solve a standard equilibrium type problem. We have a beam set here, and on that beam is hung a 250 kilogram weight. There's also a rope attached over here to a side of a wall. This beam is attached here to a pivot, so it is free to rotate. That is, there is no torque being supplied by this point right here, preventing it from rotating. The first thing it asks us to do is to go in and draw a free body diagram for the block and the beam. There are two masses here. The mass is the beam, so we need a free body diagram for it, and we need a free body diagram for the block. We do the standard way of drawing any free body diagram. First thing you do is isolate the body. So there's my block. My beam, and here's my block. Next, we inventory the forces with 1F. We have weight right here in the middle. I call that W1, and we of course have weight on the block, which is W2. Then we look to see applied. Well, I've got this pivot force here, and to make it a little easier to see, I'll change colors. The pivot force can be in any direction, and it can have any magnitude, and I don't know what it is. So when you have a force like that, replace the force with a magnitude and unknown angle with two components, a y component, x component. This will make the mathematics much simpler, and when you want to find the magnitude, you can take the two sides of the triangle and use the Pythagorean theorem to find the hypotenuse. So for this pivot, I'm going to say that there's a px, and that there's a py. And what other forces do I have on here? Well, do I have a normal? No. Do I have a tension? Yes. I have a tension here coming down. I'll call that T1. Now, who's doing that? That's the block. Therefore, the beam is pulling upwards with the tension T1 by the third law. There's also a tension this way, T2. Who's doing that? The wall. But I'm not drawing the free body diagram of the wall, so I won't have an arrow to show on that. Friction. No friction. Weight applied, normal tension, friction. Draw all the arrows. Arrows are all drawn. Next, got to put an axis. To put an axis, we'll come over here, X and Y, and we need a positive direction for a torque. I'll put my torque axis like that. It's not actually going to rotate. You can choose it either way. I had a teacher when I was in engineering school who made me always do mine counterclockwise. And over here we need an axis for this part. Again, they're not moving, they're not connected in motion anyway, so you will find it almost with no exceptions. The best way will be to draw your X and Y axis horizontal and vertical to make the math simpler. The last thing we need to do, we need to go put in critical angles and dimensions. Now that means we need to put in angles and dimensions for finding torques. I'm going to need this dimension here. And that dimension is L/2, or half the length of this bar. And I also need the dimensions over here for calculating the moment arm. And that's also L/2. Now, you're also going to need some angles. And the angles you need depend somewhat on which torques you're going to calculate and whether or not these forces are aligned with the X and Y axis. All the forces are aligned in this problem to the X and Y axis, so I'm not going to need any angles to break them into components. But I am going to need angles to calculate the perpendicular component with respect to these lever arms. I'm going to need this angle. Now, when this guy was laying flat, this W was aligned with this black line. And then I tilted this green bar, and with it I tilted this black line. So this angle right here, that is theta. And theta is this axis, and it's 50 degrees. Likewise, this is theta. And so is this. You might think I might need some angles here. I won't if I'm planning to make my torque calculation about here, because if I do that, then it turns out that there'll be no moment arm to these two. So what angles you need somewhat depends on where you plan to calculate torques. If I'm not sure, I'd just go in and put some angles in here anyway, just in case. So there's theta. And remember, this thing was 90 and I rotated it 50. When I did that, this black line here was originally aligned with the red line, and it rotated over and ended up over here. Alright, my free body diagram is done. I've got all my forces, I have all my angles, I have all my critical dimensions, I have a good axis set. Now all I got to do is read the drawing. So what's the next thing they ask? They ask me to find the tension in each string and the components of the force where the beam is pinned to the wall. Well, I've got enough room up there to find these forces using Newton's law, so I'm going to start back up here where I can see my drawing. So part B. On this free body diagram over here, I have the sum of the forces in Y is 0. And those forces are minus W2 plus T1. Reading this diagram right here. That tells me that T1 is M1G. Now I can go back and find, M2G. I can go back and find the mass of that block. In fact, I was told it. The mass of that block, it says, is 250 kilograms. So 250 kilograms times 9.8 will give me the tension in this string. Now you may say, well, I didn't need to do that. I could have figured that out without this. And I agree, this problem is simple enough, you probably could. But more advanced problems will not be simple enough to do that. So you should follow it in a systematic manner that ensures that you always get the problem right, no matter how complicated a problem may come. And in that sense, you build good habits. And the tension is 2,450 newtons. The next one that would be useful to do is, since I know T1 and I know W1, I could find PY. So we'll find that. And I'll do that over here. Let me get my picture on the screen here. Sum of the forces in Y is equal to minus T1 minus W1 plus PY, and all of that is equal to 0. So PY is equal to T1 plus W1. So PY is equal to 2,450 newtons because that was a 250 kilogram weight pulling down. But it turns out that the weight of this beam, I believe, is exactly the same. It says that the beam is also 250 kilograms. So we have 2,450 newtons for T1, but we also have 2,450 newtons for W1. So PY is going to be equal to 4,900 newtons. If we sum the forces in X, put them to 0, we'll get an equation, but we will not be able to solve it. This equation says that Px minus T2 is 0, as they're the only two forces in the X direction. So Px minus T2 has to equal 0. Px minus T2 is 0. So Px is T2. Problem is I don't know T2. We need to find T2. How can we do that? Well, the way we can find T2 is this. If we were to choose a point right here and do a torque, Px and Py would not enter the equation because they have no moment arm. We would only have these forces, W, T1, and T2. Well, I know every one of those but T2, so this would enable me to calculate T2. Let me do that. Sum of the torques about point P is 0. Those torques are first W1. And I'm looking for the perpendicular component, which is in this direction. So that's cosine theta times L over 2. That's the moment arm. And it's pulling the bar in the negative direction. Minus T1L. Let me show you that. T1, and the moment arm is the whole bar, which is L. And I'm looking for this side, that's the cosine. And then, going back up here, I have T2. Perpendicular part is this side right here, so that's the sine. And again, I have L. And that's in the positive direction. I immediately see that I can cancel all the L's. So T2 sine theta is equal to W1 times over 2 plus T1, all of that times the cosine of theta. So T2 is equal to W1 plus 2T1 over 2 times. Sine comes over and I get tan of theta. Now, we found that T1 was the weight, and we got 2 times, so this is 3 times the weight, or 3 times 2,450. And then we divide by 2. And then we divide by the tan of 50 and get 3,084 newtons. But that means Px is 3,084 newtons. So I found all the components of the pinning plus both of the forces of the string. Now, had they asked me to find the actual force of the pivot, what I could do is I could say, look, I know it's 3,084 newtons here, because that's Px. And I know that up here, it's 4,900 newtons, that's Py. And I could find the hypotenuse to find P, and I could use the tangent to find that angle there. All right, I'll see you in another video.